Good evening, everyone. Welcome to this episode of the story of mathematics. We are going to take different incidents in the progress of mathematics over the years, right from the beginning of civilization, and we're going to discuss them in a fun, playful manner, uh, from which we can enjoy as well as learn some aspects of how mathematics evolved over time. Today is our first episode, and we are going to discuss a nice, interesting story regarding cubic equations, how cubic equations came to be solved. There was once a time when cubic equations had no solution. Mathematicians had absolutely no idea how to solve a cubic equation. And by cubic equation, let me first explain what I mean. It's basically an equation of the form x cubed plus a x squared plus bx plus c equal to 0. And all the coefficients of the x's can either be a number, positive or negative, or it can be 0. And if it is 0, or it is negative, or it is positive, depending on whether they are negative or positive or 0, they fall into different classes of cubic equations. The first person of notable interest who worked on solving cubic equations was Omar Khayyam. And remember, Omar Khayyam lived in the 1000s. Okay, in his basic lifespan was from 1048 to 1131 AD, that is. And that was not a time for algebra. Algebra had not evolved. It has just been discovered. It has just been discovered by in a book called Hisab al-Jabr al-Muqabla. And Omar Khayyam did not use algebra to solve cubics. Let's get that straight. What he used instead was geometry. In fact, he used a little bit of Islamic algebra. He used Babylonian and Hindu arithmetic, and he used Greek geometry. Rubaiyat, which was his most famous work, contains a treatise on how he managed to solve the cubic. Rubaiyat was written in quatrains, which means that 4-line verses. Okay, and Franz Wopke published Omar Khayyam's famous work. It was translated in 1931 by David Castle. Omar Khayyam spent majority of his time in royal courts, and the most important thing that it did of mathematical interest was creating the most accurate calendars. Okay, mathematicians of the Islamic Empire were basically descendants of the Greek mathematicians who existed in the previous 5 centuries before Christ. Al-Khwarizmi, who is credited to be the father of algebra, lived from 1780 to 1850, and it was because of him that we can today solve equations, whether cubic or quadratic or quartic, in the manner that we do. Before that, people either knew arithmetic or they knew geometry, and it was a great hindrance in the path towards the development of mathematics until Al-Khwarizmi came up with his algebra. So we have to move forward now. We move forward to the 1400s. 1400s was the time when mathematics had come back to Europe. You know, there was a time in ancient Greece where geometry ruled the mathematical world, and then the Arabs took over. They, they created algebra. They brought mathematics forward, and then using the Arabic numerals and the algebraic techniques, the Europeans again revived their mathematics. One person of very special interest, whom all of us know, is Leonardo of Pisa, popularly known as Fibonacci. Fibonacci is famous for the series that we often use in mathematics and computer science, which basically sums two terms and gets the next term. So the first term and the second term are added to get the third term. The second term and the third term are added to get the fourth term, and that's how the series progresses. And the other important thing about the Fibonacci series is that as it approaches infinity, as the cardinal number of the term approaches infinity. By cardinal number, I mean the nth term, where n approaches infinity. The ratio of two successive terms approaches the golden ratio, whose value is 1.618. So there's a lot of mathematical fireworks happening. Mathematics really took a turn gained a lot of momentum from the Middle Ages, which started from the 1400s. And Leonardo of Pisa or Fibonacci had a lot to do with that. And another very important contribution that he made was that he popularized Arabic numerals in Europe, where the church had forbidden the use of Arabic numerals owing to the Crusades. The church was of the opinion the use of Arabic numerals was going to destroy the Europeanness of the academia, and it was going to be an Islamic influence over their culture and their civilization. But as we all know, knowledge has no boundaries, right? Knowledge has no, you cannot partition knowledge into Islamic or European. Knowledge is knowledge, and you have to let it flow. And the church was wrong. And thanks to Fibonacci, the Europeans did get to know their algebra and let mathematics progress. And thanks to that, we later had Newton, and we later had all the great physicists and the mathematicians that we know. Getting back to the cubics, right? The first formula for a class of cubic equations, remember, class of cubic equations is basically a categorization of cubic equations based on the coefficients. For example, x cubed plus bx equal to c is a class of cubic equations. Then x cubed plus a equal to bx is another class of cubic equations. And likewise, x cubed plus bx plus c equal to 0 is another class of cubic equations. So it was the University of Bologna, Bologna, which was in Italy, and Scipione del Ferro was the first person who actually successfully solved a cubic equation of the form x cubed plus bx plus c is equal to 0. But surprisingly, he hid the formula he found. That's pretty surprising. I mean, in today's times, if you find a solution or you find a formula that no one has ever found before, you don't hide it, you publish it, you post it on social media, you popularize it, you tell the whole world that you have found the formula, right? So why did you hide it? The reason is, in those days, jobs in academic institutions would be uh, recruited in the form not in the form of competitive exams as we have it today, or in the form of interviews, but in the form of duels, right? So the candidate for a job had to invite another candidate in a mathematical duel. Now we know of duels in from novels like The Count of Monte Cristo or Three Musketeers. Duels were pretty common in Europe, but the duel that we know of is a physical duel, a duel with swords and daggers and shields, and it's a duel between two individuals to show their military might. But this was a mathematical duel, and it was about mathematical might. It was about the might of the brain, right? Of the human mind. So the candidates would invite each other to a duel, or they can even invite a person in position, right? He can invite a professor to a duel, and if he wins the duel, he will get the position the professor is currently holding, and the professor will be jobless. Just imagine, that is amazing. So that's what Del Ferro was scared about, that if he published his work, then somebody would challenge him. He might develop another formula even better than his and defeat him in a duel. And that is the reason he wanted to hide his formula. Okay. So the only person he told it to was his successor, Annibal della Nave, and his student, Antonio Maria Fior. Okay. So this student of his, Antonio Maria Fior, in 1535, he invited Niccolo Tartaglia to a duel. See, this is bound to happen. If you know the formula, you're obviously going to invite somebody to a duel because you believe that you know the answer, and the person you're inviting doesn't. But in this case, Tartaglia had some idea of how cubics are solved, and he worked day in and day out, and he knew Del Ferro's formula, and he won the duel, right? Amazing. He won the duel. We have to talk about another person here, another professor. His name was Cardano, Gerolamo Cardano. He was an established professor, and he wanted to see Tartaglia's formula. Tartaglia agreed, provided he was not provided Cardano would not publish his formula. And Tartaglia also agreed when Cardano proposed that some of his works would be shown to the court of Milan. Cardano also himself worked on other classes of cubic equations. Now, the thing what happened is Cardano was very curious. He wanted to know more about how Tartaglia came up with the solution and stuff like that. So what he did was he went to Bologna, and he met Nave. You remember Nave, right? Nave was the person Del Ferro had told the formula to, right? He was the successor of Del Ferro, right? And Cardano talked to Nave, and he found Del Ferro had found the solution even before Tartaglia did. Now he had lost faith in integrity. He decided he's going to publish it. Again, we have to talk about another person in this case, Lodovico Ferrari. Lodovico Ferrari was a student of Cardano. He gave Cardano a newly discovered formula of the quartic. What is a quartic? Quartic, just like a cubic, is an equation, but in this case, the highest power of x is 4 instead of 3. So a quartic equation is of the form x to the power 4 plus ax squared plus bx plus c is equal to 0, right? And Ferrari had found a solution to the quartic. So in 1545, Ars Magna, A-R-S, M-A-G-N-A, was published, written by Cardano, and contains both the formulas proposed by Tartaglia and Ferrari. Done. Tartaglia is furious. He wants to challenge Cardano in a duel. Well, this is not to get a job. This is out of anger. He just wants to finish Cardano. Cardano has to defend himself, right? So how does he defend? He employs his student. Who is the student? Lodovico Ferrari. Ferrari invites Tartaglia to a duel. Ferrari wins the duel, right? Okay, that's about the story behind the cubic. There's an interesting aspect of the cubic, or the solution that Cardano published in his book Ars Magna in 1548. If you look at the equation, it contains cube roots and it contains square roots of what? Of some expressions made out of the coefficients of the equation. So basically the formula is cube root of square root of minus a by 3 whole square whole cube plus b by 2 whole square or something like that. It's a pretty complicated thing. You will not understand it unless I write it out, and I'm not writing out anything today. I might write out stuff in my next videos, but this is simply a one-on-one story that I'm telling you. Okay, so the main point here is that there were solutions. There were expressions in the formula which created square roots of negative numbers. So if we consider an equation like x cubed minus 15x minus 4 equal to 0, we will get square root of minus 121 if we apply Cardano's formula. But then as we go along and simplify it, the square roots of negative 121 cancel each other out in a beautiful way, and we get a whole number. We get a whole number. The point is not we get the whole number. Point is, why did the cube root of negative numbers arise in the first place? And is there a way around it? Mathematicians at those times had no idea what was going on. They had no way, they had no idea how to interpret. They were completely, I would say they were scared. They knew that they had to use the cube root of negative numbers to arrive at the solution, but they attached a lot of stigma to it. They tried to hide it as much as possible. Okay, and it was Raffaello Bombelli, who was another Italian mathematician, who actually showed us that these expressions are always in complements. So if we have something called square root of minus 1 plus 2 in one part of the formula, we will definitely have square root of minus 1 minus 2 in another part of the formula, and the two terms will cancel each other out, leaving us a nice natural number or a whole number. Uh, in spite of that, the stigma that uh, was attached to these numbers did not go away. And it's only in the 18th century that Leonhard Euler, he connected these numbers with the theory of functions. He did not have a geometric approach uh, and did not know what it represented, but he realized that uh, that these numbers were the roots of something called the fundamental theorem of algebra, which is basically that the nth degree polynomials, any nth degree polynomial with whatever coefficient whatsoever, will always have n complex roots. And all of those roots may not be different. There may be similar roots, there may be repeated roots, but the point is there will be n roots to a polynomial having nth degree. What do you mean by nth degree? The highest power of x is n. So in case of a quartic equation, the polynomial is of 4th degree. In the case of a cubic, it's of a 3rd degree. Euler believed this was true. He had an intuition it was true. He could not come up with a proof. To get a proof, we had to wait a little longer for Carl Friedrich Gauss, right? It was Caspar Wessel, who was a Norwegian mathematician of the 18th century, who actually told us that these numbers, the square roots of negative 121, or the square root of negative 1 for that matter, are not illegitimate numbers. They were not something mathematicians need to be embarrassed about when they use it. They can freely use it in their calculations, and they make calculations easier, they make calculations more simple, and they create avenues for further discoveries in the field of numbers and in other fields as well. So this primordial soup of complex numbers was now filled with confusion and competition, and people began to interpret it in different ways. They involve religion in it, they involve culture in it, and they did they treated it in every possible way except mathematical. But thanks to Wessel, thanks to Gauss, thanks to Cauchy, thanks to Riemann and Weierstrass, complex numbers emerged as a separate field of mathematics, and today it is used for studying prime numbers, for quantum physics, for radar technology, for building planes, for so many purposes. And this is absolutely fascinating. We started our episode with how to solve a cubic, and look where we ended. This is the magic that mathematics gives us. We started something, we ended something else. That's called progress. That's called civilization. We'll come back again another day with another nice story on this new channel that we are launching. And I hope you like this episode. Please join us again. Till then, goodbye. Thank you.